Hello guys and welcome to my YouTube channel. In this video I'm going to explain the PN junction.
We are taking one of the most abundant raw materials on Earth and re-engineering it into complex architectures capable of processing billions of operations in the blink of an eye. We're talking about a leap from the macroscopic world you and I can physically touch all the way down to the hyper-precise manipulation of individual atoms. So here is our roadmap for the breakdown. First, from sand to silicon. Second, a magic of doping. Third, meeting at the PN junction. Fourth, forward and reverse bias. And finally, making the semiconductor. Let's get to it. Part 1, from sand to silicon. Okay, our starting line is silica sand, which we refine to extract pure silicon. Now, if you zoom into pure silicon at the atomic level, you're going to see this incredibly stable diamond cubic lattice structure. Each silicon atom has 4 valence electrons, and it uses every single one of them to form super tight covalent bonds with its neighbors. Because all those electrons are securely locked up, there are basically 0 free electrons available to carry an electrical current. Seriously, at absolute zero, pure silicon is a near perfect insulator. It doesn't conduct electricity well at all. It is literally a blank canvas, just sitting there waiting for us to give it a job. Which brings us to part 2, a magic of doping. So since pristine silicon is basically a dead end for current, we actually have to intentionally break its perfect symmetry to make it useful. Enter doping. Doping is just the process of sneaking tiny, calculated amounts of impurity atoms into that pure silicon crystal. By throwing these impurities into the mix, we disrupt the electron balance and suddenly unlock the material's electrical potential. We can literally dial its conductivity from basically 0 all the way up to levels that rival actual metals. Let's look at exactly how that happens. When a silicon atom gets swapped out for a boron atom, which is a group 3 element with only 3 valence electrons, it comes up 1 electron short when it tries to bond with its 4 silicon neighbors. This missing electron creates a vacancy. We call this a hole. Now, here's the really cool part. Even though it's technically just empty space, this hole can actually move through the lattice as other electrons rapidly jump in and out of it. To an outside observer, that hole acts exactly like a positive charge carrier moving through the crystal. This whole process leaves us with 2 distinct, newly modified materials. On one side, we've got the p-type material we just talked about. Thanks to group 3 elements, like boron, we get missing electrons, which means positively charged holes. On the flip side, we have N-type material. To make this, we drop in group 5 elements, like phosphorus or arsenic, which come packed with 5 valence electrons. 4 of those bond tightly with the silicon, but that leaves 1 extra, weakly bound electron totally free to roam around. So, to summarize, N-type is packed with free, negatively charged electrons, while p-type is full of positively charged holes. Moving right along to part 3, meeting at the PN junction. Okay, so what actually happens when you physically mash these 2 distinct materials together? Well, this is where the real magic kicks in. The second the N-type and p-type materials touch, a massive concentration gradient triggers absolute microscopic chaos. Think of it like dropping a drop of ink into a glass of water. The excess free electrons on the N side immediately rush, or diffuse, straight over to the p side. At the exact same time, the excess holes on the p side rush over to the N side. But remember, the impurity atoms themselves are physically anchored in the crystal lattice. So when an electron ditches the N side, it leaves behind a fixed, positively charged ion, and when a hole leaves the p side, it leaves a fixed, negatively charged ion in its wake. Now, all those newly exposed fixed ions create an intense electric field right at the border, and this field rapidly becomes so ridiculously strong that it physically shoves back against any further diffusion. We call this standoff boundary the depletion region because, while it is completely depleted of any mobile charge carriers, it acts exactly like a microscopic wall, a built-in potential barrier that violently stops any more electrons or holes from crossing, unless they get a solid push from the outside. Which brings us to part 4, forward and reverse bias. We can actually manipulate this microscopic wall using an external voltage, like a battery, a process we call biasing. In forward bias, we hook the positive terminal to the p side, which forces the holes and electrons directly toward the junction. This gives them the energy they need to smash through that built-in barrier. The depletion region shrinks, and boom, current flows freely. But if we flip the battery around into reverse bias, it actively pulls the holes and electrons away from the junction instead. the depletion region drastically widens out, building a massive high resistance wall that blocks almost all current from getting through. This exact dual behavior, letting current flow easily in one direction but completely slamming the door shut in the other, is the absolute fundamental behavior of a diode. Forward bias acts practically like a short circuit, and reverse bias acts like an open circuit. That simple ability to turn electrical signals on and off with blinding speed just by tweaking the voltage, that is the foundational bedrock for rectifiers, LEDs, and the billions of tiny transistors firing inside your computer's processor right now. Finally, part 5, making the semiconductor. Taking all this incredible atomic theory and applying it industrially requires an insane level of precision. First, we refine raw silica sand to extract incredibly pure silicon. Then, this molten silicon is carefully grown into massive, single-crystal cylindrical ingots. Once they cool down, these ingots are sliced into paper-thin discs known as wafers. It's actually wild. These wafers are often sliced thinner than a single strand of human hair, yet they remain structurally perfect crystals. Then we get the most critical step of all, carefully injecting our dopants to create those N and P regions we just talked about. To get those specific impurity atoms perfectly slotted into the silicon lattice, manufacturers lean on two main techniques. The first is thermal diffusion. They literally put the silicon wafer into a high temperature furnace filled with dopant gases, and the intense heat lets the impurity atoms just soak and permeate right into the crystal over time. The second method, which gives us the ridiculous precision needed for modern integrated circuits, is ion implantation. Here, dopant atoms are ionized, accelerated in a high energy beam, and literally shot point blank into the wafer at hyper exact depths and concentrations. We really need to pause for a second and just grasp the scale of what we're talking about here. We aren't just building one little PN junction in a lab, we are executing these incredibly complex chemical and structural changes on a nanometer scale. Think about it. A single modern microchip, which is usually smaller than a standard postage stamp, packs in billions, literally billions, of these precisely doped microscopic junctions, all firing in perfect unison. There's a great saying in physics that without any conductivity, pristine semiconductors are dull stuff, but about as interesting as a paperweight. And it's so true. Ultimately, without the intentional, highly controlled magic of doping, this incredibly refined sand would just sit there doing absolutely nothing. It is specifically our ability to intentionally introduce imperfections that gives this material its limitless power.
Thanks for watching this video, guys. Please don't forget to like, share, and comment below. Also, subscribe to my YouTube channel for more videos.